And working groups, of course, groups of two people. And when you work in groups, it's always a good idea to have two versions of the code, so such that not only one person is working, but whatever you discuss something, and then you both write the code. Now, who still has problem with that? You have one problem. Who else is not able to run the code? 2, 3. Okay, I will go case by case. So only 3 people. The rest are able to get the same thing, right? Everyone? Okay, except 3 people. All right, I'll go try to help that. Thank. Okay, so for people who, I think there is only maybe 1 or 2 people who still have problem running the code. So they can catch up a little bit later. At the moment, we will focus on example, because I will give you time later to run and to write some code. I think the best thing to do now is to go back to the algorithm that you want to implement and explain how it works, and then we will we'll write the code for that. So, desktop, MLSS on Algiers, and then it's kind of a mess. Okay, so I'm going back to my lecture, and I'm going back to the algorithm of Qlearning. At this moment, I want everybody to pay attention to this algorithm. We will understand how it works from an algorithmic point of view. Then we will just translate the algorithm into code, and we will run it on the example. That's basically the whole practical session. And since I'm not covering something very advanced or complicated, I want you to really understand everything. That's the reason I made everything easy or simple. It's because we want to master this algorithm. And at the end of this lecture, you will go home knowing that you already implemented reinforcement learning technique and you made it work, which gives you psychological confidence to use it for other problems if you want, or to learn much more other things. So let's go back to this algorithm and explain how it works. This is actually the policy improvement. The Qlearning is a few slides later. That's what we want to implement. So what we have is what we have as input is, I'm going to go step by step. What we have as input is Markov decision process or model, and it's defined by 3 elements: state, space, action space, and the reward function. In the code that I gave you, all these elements are already defined. I defined the state space, which is the position of the quadrupter in the grid. The action is go left, go right, go up, go down, so it's movement. And the reward function is number, which could be either 0, 100, or negative 100. That's the example that we have. The only thing is that we don't know transition function. You don't need it. You are not going to need it because your agent is going to learn how to act without knowing the transition function. It will learn directly from data. So we have an initial state. We have this thing, which is called time, t. And this counts the time, basically, or how many actions we did. It's initialized at 0, and then it's increased each time we do something. So basically, there is this big loop where we just repeat the same thing, and each time we increase time. Okay, so we go from t to t+1, etc. And then you can stop whenever you want. So basically, it will converge to finding the optimal solution or optimal path, but you can just stop it wherever you want. So the first thing that there are a couple of things that we need to keep in mind, that we need to keep in memory. So things that we need to keep in memory are the following. So we need to have a policy, pi. So policy pi is a function. It's like function in C++ or Python, or that takes as input state. So basically it takes as input position of the robot, and it returns the best action to do. Okay, and how does it know what is the best action to do? The best action is based on something that we call the Qvalue, and the Qvalue is a table. So this QSTA is a table or matrix that has states in one dimension and actions in the other dimension. And given some state and some action, it tells you how much rewards you think you're going to gain by doing this. And this is something you learn from data. And the way we learn it is based on this huge equation that you have at the end. So we'll get to it in a minute or two. So based on these Q values, we choose the best action. And then we do not necessarily execute the best action. So what we do is the following. We toss a coin. So we take a coin and we toss it. We flip it. And then if it falls on face, pill, we choose that action. If it falls on face, or heads or tail or heads, okay, one side or another of the coin, we choose either to execute the action or to do something random, something completely random, just random action, okay? And the reason we do these random actions, of course, we do them with very small probability. So the probability that we are going to be doing something random is epsilon. Maybe it's 0.01% or just 1% of the time. And we do these random actions from time to time in order to discover new things, new solutions. Because if you do only things that you think are optimal, you will not find what is optimal. Okay, so you have to try new things to improve. So yeah, so we're going to either execute what we think is the best action or do something completely at random, and then whichever way we followed, at the end we have some action and we just execute it, okay? So it doesn't matter where it came from, either random or it was actually the best action. And then we observe the reward, and the reward is not something you have to worry about because it's given to you directly by the environment. The reward is something external, okay? So there are methods in reinforcement learning that care about intrinsic reward or intrinsic motivation, but most of the time the reward is something defined by the human or by in nature or something like that, and then you just collect the reward. And then you have to observe two things. You have to observe the reward and you have to observe what is the new state. Well, the reason is because you were in state ST, but the fact that you executed this action, you changed your state. That was the whole point, right, of the action, is to change the state, is to move. So you see where you are, what's the new state, and then based on these elements, the action, the current state, the reward, next state, you will apply your Qlearning update. So it's a very simple equation. It's one line in Python that you will write. And what it does is following. You take the out for the specific state and the specific action that you executed, the current state and the current action. That's the only thing that's going to be updated, right, at time t. We will update the Q value by applying this equation. So what we're going to be doing is the following. We have this alpha. Alpha is some, let's say it's constant. It's maybe 5% or something like that, or 1%. It's a very small number between 0 and 1. With 1 minus alpha, we will preserve the value that we have. So basically, we want to preserve a lot of what we had before. So we take what we had before and multiply it by 1 minus alpha. And alpha is like 5%, 0.05, which means that 1 minus alpha is 0.95. So the majority of the new value comes from the out value, plus alpha times the new data, the observation that we have. And the new data that we have is an immediate reward number. That's just the immediate reward. But then there is the new state that we ended up in. And for that new state, we already have its Q value, okay? The Q value that we have for ST plus 1 is not necessarily the right Q value because this one is also being learned, right? This one is also being estimated. So we are using the Q value for next state, multiplied by gamma, add to it the reward, and then you get the new date, the new number here, the observed reward, and multiplied by alpha and get the new Q value. Okay, so basically you just have to look into this equation and you should be able to implement it. And that's it, basically. And you repeat this, and then at some point you will observe that your agent is doing the optimal actions, in the sense that the agent is choosing the actions that maximize the expected sum of future rewards. So basically solving the reinforcement learning problem. This is the most basic and most popular algorithm in reinforcement learning, which is a big area of machine learning. And there is, of course, there are a lot of variants that build on top of this. For example, what should we do when we have continuous states? what we should do when we have a huge state space where we cannot explore everything. It all builds on this algorithm. So it's just small variations of this algorithm. So basically using features, but the philosophy is this. Okay, so now what I will do is I will take a few questions about the algorithm to see if you understood it, and then I will give you an example, and then I will explain the code that we have, and you will start implementing it. Okay, so let's start with a few questions, just to make sure that everybody. So if you have any question about this, just ask me now. Yeah? Sorry? Yeah. It's general. I just wrote end of learning and then define it as you want. It could be time, like the learning ends after 1 hour. It could be number of iterations, like after 100 iterations you stop. It could be never. You know, you would see just things like this. Means I don't care, right? We don't really care about when to stop, because in real life we don't stop until we die. Anyway. So, is there any question about the algorithm? Yes? Yeah? Yeah, you? Yeah, so alpha and gamma, they are parameters that are given as input, and you can play with them as you want. Yeah, so alpha is, if you have very big alpha, that means that it can be interpreted as probability. So alpha is learning rate, which means do you want to learn fast or slow? Of course, if you learn fast, you may do a lot of wrong things, right? If you want to learn to converge very quickly, maybe you will converge to something that's not really the best thing. If you learn very slowly, then at the beginning you will be doing a lot of bad actions, but you will make sure that you will get to the goal. So it's like going slowly but surely. When you have alpha very, very slow, means you are not changing too much. You are patient, you are waiting until you see everything. But if you have alpha which is very small, when alpha which is very high, then you will be learning fast, but maybe you will not converge to the optimal solution. And gamma is discount factor, which means how much do you care about future? So gamma tells you how much you care about next state. If you put gamma to 0, that means that I care only about reward, the immediate reward in state ST80. If I put gamma high, that means that I care a lot about ST+1. I care a lot about the future. Of course, gamma should be something between 0 and 1, right? It shouldn't be too small. Usually it's 0.9 or something like that. But at the moment, we're going to assume it's 0.9, and then we'll just run the example based on that. Okay? So alpha and gamma are inputs. Okay. Other questions? Do we understand at least mechanism, or is there something unclear? There must be some question somewhere. Don't be shy. Yeah? Good. Okay. Is it obvious? Yeah. The first value of Q. That's a very good question. So actually, you can prove that it doesn't matter how you initialize Q, as long as your epsilon and your alpha are not 0 and they have some properties, you can converge to the optimal solution. So as long as alpha is not too slow or too fast, you can convert to the optimal solution. And as long as epsilon is not 0, which means that you give a chance to every action in every state to be executed, then you are guaranteed to converge. It doesn't matter how you initialize the Q values. You can just initialize them to 0. That's the most practical way to do. Okay. So actually, that's a good question, because last time I went quickly over this slide, which is what are the conditions under which tabular Qlearning converts. So there are a few conditions. The first conditions are the following. If you have this, then you are guaranteed to converge. Theoretically, you can prove that you will find the optimal solution if you give it enough time. Okay? And the conditions are the following. The learning rate, if I sum, so the learning rate can be a function of time. It decreases, right? Alpha t is initially very high, you learn a lot, and then it goes down and down and down until at some point you don't learn. You are sure of what you have. So the sum of the alpha t from t equals 0 till infinity should be infinity. It should diverge. What does this mean? It means that your alpha t is diminishing, but not too much, right? It's not going down too quickly. And then if you take the square, it should converge. That means that it's not too slow. So the two conditions, first one means that alpha t is converging quite quickly, and second one says that it's not faster than it should be. So if you have these two conditions, then you can prove that you will converge. One example of doing this, you can just take 1 over t. Define your alpha t as 1 over t, which means that when t equals 1, alpha t is 1. When t equals 2, alpha t is 0.5. When t equals 3, alpha t is 0.3333, etc. So just take 1 over time, and then this is your learning rate. And then for epsilon, epsilon is the exploration probability, how much you do crazy things. And you do crazy things with probability 1 over square root of t. So basically at the beginning you will be doing a lot of crazy movements, but then over time you will converge to doing only the optimal actions. So this is theory. In practice, we don't respect that. So for example, in the code that I gave you, I didn't follow this notation. We can just take alpha t as constant or decrease it, and most of the time it works. So there is a lot of often discrepancy between what you read in textbook and what people do in practice. So theory is about proving that what you need, and practice is sometimes because you have specific case. So maybe you just fix your alpha t as 0.01 and you don't change it. It may work, okay? So this is a guideline, but in practice you can do different things. Okay, so other questions? There will be a quiz at the end. And anybody who doesn't get it will be required to pay for his registration or her registration fully. I'm just kidding. Okay, so there will be no quiz. Okay, so is this good? Shall we move to the example? Okay, let's move to the example. Again, if you don't understand Qlearning today, I feel sorry for, because I'm spending so much time on this algorithm, and I spent a whole day preparing. It wasn't, to be honest, it wasn't just for this summer school, but it was for my class that I teach. And I spent whole like 6 hours preparing this example. Let's play it. Good. Okay, I'm going to do something else. Sorry. No. Slideshow. Yeah, okay. I don't know, something's right. On my laptop doesn't look nice, but anyway, we'll just go with that. So, let's skip that. So let's say we have a drone or quadrocopter. This is one of those words that you never learn, like because, I don't know, there are some words that you always have problem with. And for me, it's this object. So usually I call them just UAVs, a named autonomous vehicle or airborne vehicle. So we have this drone and it's flying, and in this case this is our agent, and what you want to do is to have an autonomous drone, so it will be able to learn to go to actually I'm going to fix my presentation, sorry, because it doesn't look nice on my laptop and it's going to bother me. Okay, I can do this again, sorry. What the heck? It should be just slideshow, right? Yeah, slideshow from start. Yeah. Why is that? Okay. And show. All right, that's fine. So what we have here is we have this agent, and it needs to learn to go to target. Okay, and we have some regions where we have, if we get there, we are in trouble. We can lose our robot. Okay, so we don't want to get there. For example, there is power grid there, and there is some target. It could be anything. It could be an obstacle, building, maybe some area that you are not supposed to be in. So we want to learn how to avoid this area. Of course, this example is not really practical. This is not what you're going to do in practice to control this problem, but it's an illustration of how reinforcement learning works. In real life, what you're going to do, you have to consider continuous states, and you have to consider features. You have to consider features such that you can generalize. Okay? So one thing that you will notice about this problem, something that is strange, it will spend a lot of time just to learn how to go from the initial state to the goal state. And if you put it somewhere else, it has to learn from scratch. So if I buy this robot and they use it, for example, here in Algiers, and it was trained in New York, then it will not be able to work well. So the way you can make it work well is by using features of states such that you can abstract and generalize and make actions based on the features of the environment and not based on the location. So it's just small variations, which is using features that will make this work anywhere. Even if you change the position of the goal, if you change the position of the object, the obstacles, it will work. Okay, so we'll play this example just to show you exactly how it works. So numerically, so first thing, we can discretize the state into, and this is the example that you have in your Python code. So we can discretize the environment into, let's say, for example, 4 by 4. And how do you choose this discretization? It's based on how accurate you want to be, right? So for example, if you don't care about millimeters, if you don't care about centimeters, you just want to stay away from some region, that makes sense to discretize by 100 meters, for example, right? Or 10 meters or 5 meters. So it depends on what you are doing. Okay, so how you discretize your word is based on how tolerant you are at getting too close to obstacles, for example. Let's say, for example, I discretize this room into 50 centimeters boxes. That's enough for a robot. It can, if it sees this room as boxes of 50 by 50 centimeters or 20 by 20, it will manage to find a path, right? Because most obstacles, they are not that tight. There is enough space, right? But if it's very tight, like you are in some market, a lot of people walking, then maybe you should find a resolution to be able to find a way, to find a path. So then the actions that we have here are fly left, right, up, down, for example. And then we have a reward function. So the reward function is defined as -1 everywhere. And the reason it's -1, it means that don't stay there, go away. So that's what it means. You are here, as long as you are here, you are losing money, you are losing time, you are losing energy, right? So you need to go to your home, which is H, okay? H is where the helicopter lands. So the reason I put this -1, because any second the drone is flying, it's waste of battery, it's waste of energy, it's waste of time. So it gets penalized, okay? It's just wasting its life. So that means that this helicopter would be forced to get away from these regions and try to go to the high rewarding region, which is where we have this +10. And then you have these obstacles or dangerous places where you have -100, because if you get there, you lose your drone. You have to go there and get it back, okay? So we don't want to get there. We need to learn to avoid that. Then let's go to the next step. So is there any question about the rewards that we defined here, the reward function? Okay. Next step is initializing the Qvalue function. And as I said before, the Qvalue function can be initialized arbitrarily, and in this case, we can initialize it by putting zeros everywhere. So the Qvalue function is a function of two things, state and action. So the states that we have here are S11, S12, S13, S14, and until S44, okay? So the first index indicates the line, and the second one indicates the column, okay? So S22 is this state, for example. S23 is this one. And we have 4 actions: go up, go down, go left, go right, okay? And then the Q values, initially, they are all zeros, okay? So we're gonna go to, we can start, the agent will start learning. So the first thing is the following. Execute some random action. So at the beginning, you don't know anything about the word. I think there was a question, yeah? Oh, yeah. So the numbers in the code may be different from this example, but it's the same philosophy. The rewards are a little bit different, but it's exactly the same. So instead of using 100, I'm using this example 10. So it's not exactly this slide is not exactly the same example. It's an illustration of how it works. It's almost the same. Okay, so at the beginning you don't know anything, so what should you do? You should execute any action at random and see what happens, right? Your knowledge is zero about the word. The robot doesn't know where it is, doesn't know what it's doing, so just choose some action, and the action in this case was go right, okay? Then, so this action is as good as any other action. So we start executing this action and we try to go right, and we go right. So the robot flies to where it wants to go, and it has IMU sensors, inertial sensors, and tells it where it is actually. So it knows that it succeeded to make the action work. Okay, so it went right. And then after we did this move, we have to update the Q value of the action that we executed. Okay, so this is how we update it. I'm going to just show here the equation, how the Q value of the action that we executed got updated after this observation, after this action and observation. So how do we update it? We, since the previous Q value is 0, then, so just to show you the previous slides that I had, the algorithm. Okay, it's not here. Okay, so we said the way we update the Q value is by taking a little bit of the previous Q value and a little bit of the new observation. The previous Q value was 0, so I don't care about this first part. So I'm going to write down only the second part, which is alpha t times the rest. So this is how we update the Q value. We take the immediate reward, which is -1, plus discount factor. In this example, discount factor is 0.99, so gamma is 0.99, times the Q value of the best action at the next state. So the next state that we did go to was S12, right? It's S12. And at S12, the best action is, they are all the same, right? They all have 0. So take any one of them, it's the same. So we're going to choose the first one, go up. And it has Q value of 0, so this 0 goes back to the Q value of the previous state. Okay, so you look into the new state, you see what is the best action, and you can use it for changing the value of the previous state, S11, the previous state and the previous action that you did, which is go right. Okay, so and then this gives you -1 plus 0.99 is times 0. Okay, so 0.99 is multiplied by 0. Why is it multiplied by 0? Because the Q value at the next state is 0. Okay, and this becomes -1. Is there any question about this update? If you have, basically what I just showed here is half of reinforcement learning. 50% of research in reinforcement learning is what I explained in this slide. So if you have a question, ask me, and it will save you time later. Yes? Mm-hmm. Yeah, so when everything is the same, because initially every action has 0, yeah, then choose arbitrary, yeah, randomly, yeah. Usually in reinforcement or in machine learning, the way you break ties when you have things that are equal is by randomly choosing something. Don't choose always the same thing. Let's say you have 4 options, they are all equal, sample something randomly and do it, yeah, good? How to choose what? Louder, please. Discount factor. So discount factor is, it depends on how much you care about long-term rewards versus current rewards. Yes? I just choose it arbitrary. It doesn't make much difference. The thing is that we will play with different discount factor, and you tell me what you observe in your code, okay? We can put very low discount factor, very high, and tell me how you observe learning changes, okay? We'll get to that. Is there a question about this, please? By the way, these PowerPoints are, you have them, I sent them by email, yeah? How much is known? The value of? The horizon. This is infinite horizon. So in this problem, we don't have a limit in the future that we look for. Anything is counted, but we have discount factor, 0.99. Such when you have discount factor, you don't care about the horizon, because discount factor will make sure that things will get smaller and smaller and smaller when they are further in the future, right? Because you will be always multiplying things in the future by discount factor power to the power of how far it is in the future. right? So when you have a discount factor which is smaller than 1, then it will take care of the horizon, okay? Yes? The, which one? Which alpha, no, it's going to go down. Slowly it will go down, okay? Yeah, you cannot learn. Then you will be always ignoring the previous one. Good point. But alpha will be going down slowly, okay? You will observe that. Okay, so this is the new Q value is 1 minus, so we want you to implement this in Python later. Okay, now let's go to the next step. So we did this. Then we are now in this new state, S12. What should we do? The Q values are the same for all the actions, which means that I should just choose something randomly, right? Because I don't know which one is the best. They look all the same. So we're going to choose some action randomly, which is this, go down, okay? By chance. This is just chance, right? This is just by luck. We choose this one, going down. And the robot will start flying down, okay? It will start going there where it wants to go. And, oops, things don't happen like you want them to happen. Wind effect. Just remember, I would say something Arabic because this is what I thought about when I was doing this. I couldn't use it in the US. So there is this Arabic verse that says, تجري الرياح بما لا تشتهي السفن, which means that the wind takes you where you don't want to go. And this is an example of, in life, yeah, things that happen. And so this is what happened to this drone. I wish I was able to translate this beautiful verse to Americans, but it would lose its meaning. So the drone was trying to go down, and the wind came and it got it to this place. And this is an example of stochastic system, where when you try to do something, things don't go as you want because there are things that are out of your control. Like if you are driving a car, there is traffic, somebody can cut in front of you, maybe you try to brake and your brake doesn't work, maybe there is new wind that comes. There are a lot of things that happen. And this is not just for cars or for robots, in also software agents, you can have things like this. Yeah, there are a lot of things that we just cannot predict, right? It's impossible to predict exactly the future. So this happened, so what should we do? Well, there is nothing special, we keep doing the same thing, okay? Doesn't matter if the helicopter doesn't know if this was the wind or it just knows that I tried to go down and I died and they went there. That's all I know. So I'm gonna update the action of going down based on what I have observed, right? Which is not correct, but actually with experience, the robot will learn that, oh, that was just coincidence. That was just one-time thing. That was just small probability event, okay? So the beautiful thing about the reinforcement learning is it's exactly the same simple equation that we apply all the time. And then just from experience, from learning, we'll convert to the right thing to do. So we tried to go, we executed the action of going down, we observed something, so we're gonna update the Q value. So the which action is going to be updated? It's the action of going down, because that's the responsible action. I'm going to blame this action for what happened, going down. Okay, I'm going to update it, and the way I'm going to update it is exactly the same thing as I did before. Take the immediate reward, which is -1, multiply it by 0.99 times the Q value at the next state. Okay, so if you initialized your Q values with 0, then it's going to be, the Q value at the next state is going to be 0, okay? But to speed up this example, because we don't have enough time to do all the actions, I cheated a little bit and I initialized the Q value of the next state. If you see the Q value of S13 to already -100, okay? I initialized the Q value of this dangerous region as -100 such that we can get immediately this negative reward to the previous state. Otherwise, we will have to iterate many times before we get this information. So, so you see the cheating that I did here was the Q value of where is this power grid is already initialized to -100. It's not initialized like the other things to 0. But even if you initialize it to 0, you will, and you just keep its reward as -100, you will learn that. Okay. So this is just to speed up the example. I did this. So we're gonna update the Q value of going down, and it becomes -100. Okay. And the -100 come from next state, which is dangerous. And this is not correct, right? Going down is the right thing to do, is the best thing to do, but this will be corrected later, okay? Then, okay, now the drone is lost, so we reinitialize, we go back to the initial state, okay? So this is terminal state, take me back to the start. This is what the journey is telling you. Take me back to the start. So we go back to the start, and we start again. So now we have 3 actions that are 0 and 1 action which is -1, as you can see. So we're going to choose some action which is randomly, which is going down. Okay, so again, the best action is not clear, okay, because we have 3 zeros and 1 -1, so we don't know what's the best action. We'll be randomly choosing some action among the ones that have 0, and we will execute it, which means going down, and then we can observe what happens, which is going down actually, and then we're going to update the Q value of going down. Of course, from now on, I'm not going to show all the details. I'm going to just show you the execution and how the Q values are updated. So we have the Q value of the previous state and the action of going down updated and becomes -1. And then we can do the same thing here, choose some action randomly. And so we can choose some action randomly and then execute it. Sorry, actually, yeah. What I wrote here is general mechanism, which is use some probability epsilon, and with probability epsilon do something randomly, and with probability 1 minus epsilon choose the action with the highest Q value. And in this case, we have three actions that have the same Q value. So it's going to be a random action among the ones that have 0. So we can update the Q value again, go right, update the Q value, go right, update the Q value, go up, and all this is random. The robot still doesn't know where it's going. It's just doing things and updating the Q value based on reward and based on next state. And then beautiful things happen suddenly. So the robot just randomly goes to the right, and then it gets to a state which is really pleasant to be in, home. There's nothing like home. So it gets it gets a reward of +10, and then it updates the action of the previous state, which was the reason why it got home, okay? So, and this is the beautiful thing about reinforcement learning, is how can you propagate reward to the past such that you know what were the actions that were the cause of your happiness, okay? So what did you do in the past that led to this current situation? And that's how you update you, and then you will be repeating those actions. And the same thing with things, bad things. When bad things happen, when the robot falls, it will start blaming everything it did in the past, such that it will be avoiding that. But this is all, of course, proportional. It's not like deterministic. I did this, this happened, I will never do this again. No, it's a learning process. Okay, so we got this action figured out. When you are there, go right, okay? And then we're gonna restart and repeat this many, many times until, I will just show you quickly one example again, and then we'll get to the code. Actually, the code is very simple. It's just a few lines of code, and you will be able to see how it's learning this algorithm. So go down, and okay, so what we did is this. I'm going to go back. We are in the initial state. We choose some action randomly. We go down. We observe reward and the new state. We will update the Q value of the previous state. Currently, this goes back to your question. Alpha. Initially, it was 1, and now it's 0.8, okay? So you can see that the learning rate, sorry, I think there is an arrow here. So the learning rate alpha here is 0.8. So we're going to use this learning rate to update the Q value. So we're going to take 1 minus alpha times the out Q value plus alpha times the new Q value or the new observation. The out Q value was -1. And we're going to multiply it by 0.2. And the observation is a reward of -1, discount factor 0.99, and the next Q value of 0. And next Q value 0 comes from the next state that we went to. You compute this. This is just this equation that I am showing again and again, and this gives you a new Q value. It remains actually -1 because why is it still? Oh yeah, because you have -1 times 0.2 plus -1 times 0.8, and this is exactly -1. So it's special case, okay, where we have the value doesn't change. Okay, you get here, you do the same thing. You choose an action based on the Q values that you have. You update new state. You come here, you do the same thing, and look what happens here. So once in a while, you have this wind that takes you to regions that you are not expecting to go to. So there is some stochasticity in the system. It's not deterministic. And that's the whole reason we are not using A star. Why am I not just using A star algorithm or some planning algorithm? It's because of all these probabilities that I need to take into account, right? So that's why we are not just finding the shortest path, because I have to take into account that if you get too close here, then you may go to the power grid, and this is bad, etc. So if I am here and execute this, and let's say by chance I ended up here because there is small probability that this happens, and I will end up here, then I will update the action of going down. So you see that the action that I executed here is going down, which means that the action that I will update here is go down, because that's what I did, right? So I'm going to blame what I did for what happens. So I'm going to blame this action, I'm going to update it, in the same way I update all the actions that I do. And then I got here, and then by chance, just to speed up the example, I assume that I'm going to get this action, and go to this. And the wind takes you away again. So this wind is like playing against us. So we're trying to go to home, and then the wind takes us down, and we update this action, and then from here we go here, from here we go here. This is just, let's say by chance you do this, and then you update, you see all the Q values, how they have been updated. This is all knowledge. This is all knowing how much, what happens in the future in terms of rewards if you execute these different actions. So go back to home, take me back to the beginning, restart, do something, update Q value, go down, and this time we are lucky. We are here, we did the same action we did last time, and we ended up in this power grid, but this time we didn't fall into the terrible place, right? We managed to go down. And this is the reason why the Q value of going down is going to be improved. So the Q value of going down was negative 100, but it was negative 100 because of bad luck. We're not lucky. We were there. We did the right thing to do, and we ended up in trouble. Okay. Then we blamed the action that we did, and we gave it a reward of negative 100. But next time we tried it again because we are still exploring. So we tried doing exactly the same action again, and we see that it's not that bad. If you do that, actually, you don't always go to the power grid. You don't go to this electricity grid. You don't go to negative rewards. So often it works well. And since we are updating this action, you see that the Q value becomes negative 25, and initially it was negative 100. So you see that you should never like judge actions just based on one-time experience. You should always repeat them until you are confident that this is really bad, don't do it again, or this is really good. But the beautiful thing about reinforcement learning is that you don't even have to care about all these things. So this is just I'm explaining to you how it works. The only thing you have to do is this algorithm, this update equation, and it takes care of things. Okay, and yeah, so at the end, by doing this, you will converge to the optimal policy. Okay, and I think that's all with this example. I'm sure you have some questions. We can answer them, and then I will explain to you the code and how to implement this. Yes? Yes, in the back? It depends on what? You said the choice of the next state depends on the Q value? No, it's the choice of the action that depends on the Q value. The only thing that you get to choose are your actions. The next state is not up to you. It's up to the environment, okay? So if you are driving, you can choose to turn left or to turn right. The action is your choice, okay? And it depends on your Q value. But the actual state, what happens after you do that, that depends on your transition model, on the system, how good is your car, how good, right? So it's an interactive process. There is one step where you choose an action, you choose something to do, you execute it, and then you see what happens. And what happens is not up to you, right? No. So how do you choose an action? You are asking a question, how do you choose the action? Yeah. So how do you choose the action? 99% of the time, or 95% of the time, you will be doing the action that has the highest Q value, okay? You have this table of Q values, and then 95% of the time you will be just choosing the best one and doing it. But 5% of the time, randomly, right, you choose something at random, anything. And in order to learn the optimal policy, you have to give a chance to everything. right? You have to, in theory, you should try every action, every state infinitely many times to be able to converge, even with very tiny probability, okay? That's the theory behind. So this is what we call exploration versus exploitation. Should I, okay, so where we're going again, because reinforcement learning is so linked to philosophy and to life, I like to give a lot of metaphors in life. So let's say you are doing something in your life and it worked well. Then you face this dilemma. Should I keep doing what I was doing, or should I try something different, and maybe it's going to be better than what I was doing, right? If you just do things that you think are the best, you are never going to get the best of your life, okay? So let's say you have some plan, you follow it, you get some reward but who says that this is the best thing? You have to try something else, right? Yes? The drone doesn't know anything if it's good or bad. All it knows is what it sees as a reward, and it uses this reward to update the Q value. It's blind in this sense. It just updates the Q value based on the action that it did and the observed state and the reward. Okay. So, but do you mean how does it know the reward? So if you repeat this many times, you will see that the right thing to do will have a higher value on average, on expectation, because this Q value gets updated. And if it was only 1% of the time that the wind comes, this will diminish because it doesn't happen very often. Okay, you will get, I don't know. So let's say you want to decide if you will be driving a car or taking train. Okay, and let's say you are driving car, and the first time you drive a car, you have an accident. Okay, so you don't like doing this action anymore. But actually, if you drive for 1 year, you realize, on average, it's not that bad. It was just one time that happened, okay? It wasn't the car, it was something else. Some stupid guy who was hitting me, and it wasn't my fault. So this is the same thing with the drone or with a lot of things. Yes? Uh-huh. Sorry, the question? I think we will get to that after. You are talking about multi-agent, right? I think it's better because I'm worried that we'll not get, I'm sorry about that, but we'll take it offline and we'll discuss this. Okay, yes? Sorry, question? To the previous state? Yes, that's what happens naturally, because this negative 100 came from next state, but the next time this negative 100 will go to the previous state. Next time you come here, you will be propagating back the Q value to the previous state. So every time you take the Q value of the current state and you give it back to the previous state, which means that from previous state it will go to the previous state at some point. So it goes back to the beginning. And that's how you find the optimal policy. Okay. Other questions, and then we get to the code. But I want you to understand the algorithm, because you will be coding it now. And they will be guiding you a little, and then at the end I will show you the answer. Yes? Good. Question? Can you keep it quite a little bit? Everyone else? Can we listen to the question? Sorry. Yeah? When do we decide that it's finished learning and start using solution? So so in practice what you do is whenever there has to be a human that interferes, whenever you observe that behavior is good, then you stop. You say, okay, stop exploring, stop doing crazy things, just do the best things that you are doing. Let's say, yeah? Well, if the environment changes, that's a different story. Okay, then it becomes more challenging, right? So there are a lot, of course, other things to take into account, but we are talking about the ideal scenario here. If the environment changes, then it becomes non-stationary, then how do you transfer what you learned before to new situation? It's transfer learning, so there are other things to take into account. Other question? Yeah? Yeah, so when you update, sorry, I think I will answer it. So you just update the previous one. You don't propagate, but it will happen because you will restart from the beginning, and it will just happen naturally. But the only thing you have to update is the previous state, okay? And then the previous state, you can update it next time you will be in it, and you move, it will be updated in its turn. Yeah. Other things? Yes? How to know what? Oh, yeah. How to stop exploring, you mean? That relates to his question. So we think you can either, okay, I will answer it in a more general way. You can either define some reward and you say, whenever I have this reward, I'm good. I will stop doing things. I'm happy with what I have now, okay? It could be like this. For example, whenever I get $500 million, I'm gonna stop investing, I'm gonna just retire and stop doing things, okay? Or it could be, so this is if you define like what is your minimum, where do you want to stop naturally? Or it could be subjective. Let's say you have a human and the human stops learning. Let's say, for example, you have software and software is learning how to talk to people, okay? It's learning how to talk by reinforcement. It's trying different things and the human talks back and gets rewards. And then the moment you notice that it's working pretty well, all right, then you can say, okay, let's stop updating, let's stop learning, let's just choose the best action based on Q values in each state. Let's not update anything anymore, right? You can say, I'm happy with this policy. So there are different ways to do this, okay? Like for example, in video games, there is a lot of work on reinforcement learning to play video games from image. So you observe an image and you play some game. Whenever you see that the agent is learning better, is playing better than a human, it's playing very well, then you say, okay, I'm going to freeze the learning and we can just use this policy. Yeah. Yes? Then, yeah, so that is the case that we deal with when we use functional approximation, when we use features. In that case, it doesn't matter where you are. What matters is how far you are from the ground, how far. When you start using features, you abstract, and then it doesn't matter anymore where you are physically. So that's the extension of reinforcement, of Qlearning to using functional approximation. Actually, look into my slides and you will see. The last thing I was talking about in my slides was about that. Yeah. In programming? No, in programming we force it to stay. We assume that there is a virtual wall and it will not go out. That part we already taken care of. In your code, you will not have to worry about all these things. Other questions about Qlearning? Are you confident? Yes? Mm-hmm. Oh, yeah, okay. Good question. Go back to the beginning. Oh. Okay, I'm going to just exit this. I'm going to stop with this and then we get to the code. I will just explain why we did that. So we were here, right? And we went down. And what happens is that we ended up in the bad region because there was stochasticity in the system. There was a stochastic outcome. We ended up here, and the action that we will update is always the action that we executed. The agent doesn't know. Maybe it thinks that this is how it works. When I'm here, I try to do this. This is what happens. So you always only update the action that you did, right? Because actually, in robotics, there is a relationship between the actions and what happens in the world. Like, for example, physical movements. But let's say this is just an example. Reinforcement learning is not robotics. That's something a lot of people get wrong. So an action could be, for example, asking question. I ask a question and I hear something back. Asking questions is nothing about going left or right, okay? So for example, I'm talking to a human and I will be asking question, where do you want to go? And the human says, I want to go to Al-Harash. And then you say, well, when do you want to go? So you can be asking questions and you are observing feedback from the human. And there is no direct meaning of how my action links to what the human is going to say next. Maybe I can say, where do you want to go? And the human says, it's none of your business not to ask me, right? This could be an observation. Okay, so let's go to the, thanks for the question. So let's go to the code quickly and get there. I will give you, let's see, time first. Actually, I need my battery first thing. Okay, so everyone, if you can go to the code, it's very simple code. We can open it and see what we have there. So as you can see, there are a few files here. So this file, which is called the run, is the main one, the main file here. I'm going to close these windows just to make sure I'm working on the right. Okay, so I think that's all I had. So I'm going to just open this run. So actually, first thing I have to say is that I'm very novice in Python. I'm C++ person, and I guess maybe I'm old, and I haven't been coding in the last 3 years, so my main language has been C++, and Python is not something I'm very familiar with. But since people here prefer Python, and I think most students these days use it, so we're going to use Python. So we can start from here. We have two things that we have to worry about. First one is the environment, and second one is the learning function. So we have environment and Qlearning. So the environment, we're going to get it from this file called the environment. Where is it? It's here, yeah. And we have Qlearning, which is another file where we specify the learning. So these two components, first one with the environment, it just tells you how the agent moves. It just visualizes things and gives reward, and it's like the word. And Qlearning is the mind, okay? So it's what's going, how the agent is thinking, okay? So Qlearning is making decisions, and Qlearning functions here will be making decisions and learning, and the environment takes care of the physics and the rewards and what's going outside of the robot, okay? So at the moment, Qlearning, as you can see, I left it empty because I want you to fill that. And we'll go through the environment first, or maybe the main code first. It's very small, as you can see. So what do we have here? We have for episode in 1 until 999 or 1000. We just repeat this, okay? This is arbitrary. You can make it smaller or larger if you want, depending on how patient you are. So first thing is the following. We can get from the environment, we're going to reset the environment to the initial state. Okay? We can put the drone at initial position. That's first thing. And then we can read the state. We can get the state from the environment. State means that I'm asking the environment, where am I? Tell me where am I. Okay, we get the state, and then we're going to repeat this again. So these are all different episodes. We start at the initial state, and then we just repeat this loop. And then there are certain conditions, when they are verified, we break and we go back to a new, to reinitialize again. So what are these conditions? We break if we get to the goal state, okay? If we get home, then we go back to the beginning. If we get to an obstacle, if we hit a wall or we hit a tree, then we go back to the beginning. So whenever something happens such that the robot doesn't move anymore, then we put the robot at the beginning and we restart the episode again. Okay? So each episode is restarted if we either get to goal or we hit some obstacle. Okay? So what do we do here? First thing is getting an action using the Qlearning. Okay, so Qlearning is the mind of the robot, and you give it state. That's true, actually. I didn't even look. Sorry, I was just looking at my. Yeah. Okay, I can do this like that. Okay, that's good. Okay, so the first thing is you get an action using this Qlearning function, and this is what you want. I want you to write this function. Okay, And then what do you need to tell the agent before you get an action? You need to tell it which state it is in. So you give it as the input state, and you get an action in a return. This is policy, okay? Takes state and returns an action. What you need to write now in the next 30 minutes or 40 minutes is this function, get action. Okay, and then once you get an action, you call the environment and you execute the action. Okay, and then things happen. The drone will fly and things will happen. This is not something you have to look into, because this is something we already have in the code. It's already working. You just give an action and it will fly somewhere, and you get as output a new state where you went to, the reward, and done. Done is binary variable that tells you if you need to restart because you got to the goal, or because you hit some tree, some obstacle, or not. So this done just tells you if you are dead, or if you got home or not, which means restart. So done means restart or not. But the most important things are this reward and next state, because you can be using them to learn. Okay? So you choose an action, you execute your action, and then you learn from your action. So Qlearning learn, and this is where you're gonna write one line that updates the Q values. Okay? And then once you do this, you can update your state, because now you know that the state is whatever you got from environment as the next state, and you go back to the next step, and at the next step you repeat exactly the same thing from the initial from the current state. Okay, you go to new state and you repeat the same thing. You go to new state, you repeat the same thing and that's it. It's very elegant platform that can solve complex things. You see that this code, it could be anything. This action could be anything. This reward could be anything, and it will figure out the optimal action. Okay. So before I will let you on your own, and I will guide you basically, actually. But I want you to write that. We will open the environment. I'm not sure if it's important. It's something you can make abstract of, but basically the environment is the visualization of the environment. We have, what do we have? Load image here. Here we have some function that writes the Q values such that you can see them. You can visually see the Q values that you have. We'll get to it later. This one, oh yeah, needs to be zoomed also. Yeah, sorry. Forget about that. What is important here? We have this function which is takes state and translate it into physical coordinates. So basically, state is either 1, 2, 3, 4, and then we want to translate this into pixels, right? 50 pixels, 60 pixels, and put the agent there. Okay. So the coordinates on the image. So because we don't learn on the pixels, we have so many pixels. We learn just on these small boxes. Our state is just this box or this box. We have small number of boxes or states, and that's what the agent is learning on. But to visualize things or to execute things physically, we need to go from this abstract view to coordinates. Okay, but this is not something you have to care about. And then we have a reset. Reset means, well, put everything at the initial configuration. We have, this is the most important thing, okay? So all the rest is just, this is the transition function. What is transition function? Takes as input an action and moves, this is dynamics. This explains how things actually are working, okay? So we take as input an action, go left, right, up, down, and you can see here that we have 4 cases for the actions, 0, 1, 2, 3, and each one means some action, either going left or right, sorry, up, down, left, right, as you can see. And then based on the action and based on the state, we can do some motion. We can move in specific way. We can move either up or down or left or right, okay? And then we move once we find the movement, we move the agent. And, okay, that's it. We move the agent and we calculate the next state based on the motion. And then we compute the reward. So this is the transition. This is dynamics. This is how the robot is moving based on the action. This is the most important thing. If you change so how do we know this? Since this is simulation, then I have to know this, right? But in real life, you don't have this. What you have is real world. You have a drone. The drone flies, and it observes where it is and uses this knowledge, okay? But here we are simulating the problem, so we are already implementing how the drone is moving, okay? We already We are already implementing this. But in real life, of course, you don't have any of that. You just have Qlearning, and then you have real life in front of you. Okay, so you execute an action, and you see what happens in reality, and then you update your Q-values based on that. Okay, so then we move the agent, and then we have to compute a few things, which are, for example, the reward. We need the reward. That's how we learn. So the environment gives some reward to the agent, and reward is basically by default 0 in this. In the previous example, it was -1, but here I'm going to make it just 0 everywhere, except if you are at the goal. Okay. So the goal state, which is some specific position that we defined before, it has 100 reward. And then you got the terrible states where you get -100 reward. And that's it. And then you return your reward. Okay? And the rest doesn't matter. You have two things that you need to look into. There is this time.sleep. This is just for visualization. We're going to put it to 0.03 seconds. And this is the time between two motions. If we make it too small, you cannot say anything when you run it. If we make it too low, too high, then it will be too slow to visualize. So please play with this if you want to speed up your visualization or your simulation or not. Okay. So you can speed it or slow it based on this. And then I have also another sleep here, which is here. I put it ½ second. This is at the beginning, how much we wait before we start. Okay. So play with these two things to make things go fast or slow. Okay. So this is the environment, and then we're going to go to the Qlearning, where there is nothing. There is your understanding, and I'm waiting you to write this. So what do you need here? Okay, let's get started. This is what you need to write. So currently, what do I have here? Can somebody explain to me what I'm doing here? I have this function, which is called getAction policy. It takes as input state, and it returns an action to do. Okay? Sorry? Oh, yeah. Yes, I have short working memory. I have an LSTM of 1 unit. Okay, so the what do we have here? What are we doing here? Sorry? Random action. So basically, we are just crazy, just going in it, doing anything, right? So we are just choosing a random action and executing it. And this is what you see from here. So it's just doing random things. And then whenever it falls into these trees, it stops and we restart the problem. We go to the beginning. And then it will take forever to get to the goal by chance, by just doing random motions. Okay? Eventually it will get to it. This is the worst possible thing. This means that you are not doing anything, you are not learning anything, you are just doing random stuff. So let's improve this. Let's make the agent intelligent, and let's make it learn from its experience. So let's do this. We have to, inside here, you have to define alpha, define it as you want, okay? Learning rate. So the thing is the following. I want you to think about this problem as your problem and solve it, because this is the best way to learn. It's not by listening, but by solving the problem. So implement the Qlearning algorithm here. It's just like 20 lines of code, maybe 15 lines, I would say. Start doing it, and then after some time I will check how you are doing. But what you need to do here is you need to most important thing is the Q table. Okay, define a table that takes as input states and action, initialize it to 0, and then update it each time you get some feedback, and choose your actions based on that. So I want you first at the beginning to start thinking about this, and then I will give you an answer. Okay. So in terms of time, it's 5, and we're supposed to. When did I start? 3:30? 4? 3:30? Ah. Half an hour. Maybe I should just give you the answer. No. No. You have to think about it for a little. Okay, let's see if you are champions in coding and see if you can do it in. Were we supposed to finish at 5:30 today? Ah, okay. Yeah, sorry. Sorry? Yeah, we can choose them. You know how we can choose them? You know how we're going to do it now? I'm going to show you the answers, and I want you to write it as I'm writing it, and then you will be running the code and see that you will implement it. So I will guide you how to do it, because half an hour is not enough for you to write the code. So since I'm professor, I'm going to cheat. I'm allowed to do this. You are students, so you shouldn't. So I'm going to look into the answer. And where did they have the answer? Qlearning, Qvalue, master, whatever. You are also professors, I know. So, but anyway, you are playing the role of students. Must be at desktop and MLSS Algiers and Qvalue and Qlearning. Okay, I have it here. Okay, so I want you to write this, but we can do this, okay? So put your fingers on your laptops and start looking into this. This is initialization. So we can initialize certain parameters in this class, which is called, so it's not a lot of code, 40 lines. We can do them and explain them in 30 minutes. And you will be implementing your first Qlearning algorithm. So first thing is the following. So write this and think about it, 5 minutes. And tell me what we are doing here. Write this, you don't have it on your code. Please write down this. And as you are writing, think about it and tell me, try to reverse engineer this code. Tell me what you are doing there. Think. Everyone's supposed to do that. So the first one to do it will come here and explain what they did. Who is done? Come in. Okay, we just give you the mic and you can explain. We're going to make this interactive way. Yeah, explain what you wrote.
Okay.
You know something called monkey coder? There is this term. It's slang for some people who are just coding. They don't know what they are doing. It's not. So we can show that we are doing. We know what we are writing. We know what we are writing down.
So if you remember the algorithm, when we update, we go from a state to another, we have to update and propagate the reward, right, to the previous state. So the alpha, the factor alpha is here. We initialize all our parameters. So the alpha, the gamma, and the epsilon rate, all those rates have to be initialized, and also the initial Q table. And initially, all states are to 0. So all have reward of 0. There is no information about the environment at all. And
why did you choose alpha 0.01?
This is how, what we done in the previous.
Sorry?
Why we have choose this?
Learning rate, but why is it 0.0? You don't know?
No.
Say it. Say it to the mic.
So it starts slowly, but for the exploration versus...
It's not exploration, exploitation, that is epsilon.
Oh yes, the epsilon, yes.
Yeah. How much you change your Q values, right? You want to change them slowly. You don't want to change them suddenly because of sudden changes, okay? So this means that things will be changing slowly. And okay, gamma is 0.9, that's arbitrary. Actions is just the actions that we got as input when initialize, and then this is given to us. And then epsilon, we choose it as 0.1. What is epsilon? That's a very important question. What is epsilon for everyone?
For the random, when we are in a state, we can choose actions, and if the rewards of each action actually is less than epsilon, then we choose randomly.
It's not the reward, okay. So
the
probability, so we sample number between 0 and 1, right? If it's bigger than 0.1, then we do the best thing. If it's smaller than 0.1, then we do something at random. 0.1 is the proportion or the frequency of doing crazy things. Means that 10% of the time you are crazy, 90% of the time you are rational, you are doing the best thing, right? 10% of the time you are trying random things to discover solutions, and 90% of the time you are doing what you think is the best, which is not necessarily the best, it's what you think is the best. Okay, so 0.1 means that 10% of the time, on average, out of 10 actions, 1 action is going to come as random, okay? If I put this epsilon to 50, then the robot will be doing a lot of random things. If I put it to 0, then the robot will be just executing the same thing and never trying anything new. Q values is initialized to 0. Did everybody write this down? Moving to the next step. Write, get action. Okay, for that we have to break it into let me see how I can break this into, maybe I will just ask you to write it and explain to me. Okay, let's write the first case. Oh yeah, that's good. So let's write function, this function, and write just there are 2 cases, and write the first case and then explain to me what it's doing. At the end, you're going to run your code, and it should be learning. You're welcome. So I hope you are writing, or you are done with writing, and because that's important. At the end, you will compile everything. You will run everything, and you will be happy, and you will get your reward, and you will learn about reinforcement learning. Yes. No, just the if. And then we go to else. Yeah. Yeah? Why did we add the max? Okay, I need volunteer, and we'll try to explain, and then if you still have the question, you just ask it again, okay? Yes? We have another champion. So can you take the mic and explain this code line by line? You can come here, actually, and use this to highlight things. Turn it on. Yeah.
Where's the highlighter? So first we choose we generate a random value. If it's greater than epsilon, so it's how would I say it? A valid action. We choose the action which is best to the Q table. Here the action values.
Okay, just a second. So what we are doing in the first line is we randomly generate or uniformly sample some number that is between 0 and 1, like 0.556 or something like that, between 0 and 1. And then if it's bigger than 0.1, then we'll be doing the best thing to do. If it's smaller than 0.1, then we'll be doing something random. We'll get to it. So here, if we happen to be having a value bigger than 0.1, then we'll be choosing the best action, and that's what we'll be doing here, okay? So this is how you implement a random exploration policy. The only thing that we have to know is that this function, a random uniform, gives you some number between 0 and 1. And this epsilon is some number that is equal, for example, to 0.1. Okay? So if you increase this to until 1, then this case never happens. Let's say epsilon is 1, then we can never have a number between 0 and 1 that is strictly bigger than 1. Okay? Let's say epsilon is 0. If epsilon is 0, that means that this condition is always verified. We'll always be doing this. These are the two ends of the spectrum. Okay, go inside this. Yeah. So of course, I'm going very slowly. Like you never see, it's extremely slow the way I'm explaining, very detailed. But I think it's good to remember this experience because I noticed a lot of people, they read a lot of things superficially. I'm guilty of that myself. I think it's good to have to spend. It's worth spending 30 minutes, and then you will know that you know for well reinforcement learning for the rest of your life.
So in this instruction, we set our action. So we have a state, which is the input of the function. We have our Q table already initialized, so we choose an action. We initialize an empty list. So here we will fill it. So here we loop. We choose over the available actions. How we choose? This is the argmax. This is the first line in the algorithm presented. This is the Q. The pi. So here, this is the pi. It is the argmax of the action values. So here, we test from the action values if it's the maximum. So the argmax actions, we will add it to our argmax list. And here after we finish looping, we make sure that we have the maximum from the maximum values of the action states. We choose from we have here argmax list. We randomly choose one as our next action.
Good. Thank you very much. Okay. So I will go over it again in case something was not clear. So line by line, just quick again. So first thing we're gonna do, we're gonna extract the values of the actions in the current state. I mean this state, which is called state, I care only about this state. I want to find what to do here. What to do next is going to be next time for the next state. It's going to be another time. But now I am in state, so I'm going to extract this table or this list, which is called action values. So if I have 4 actions, I will have 4 values. If I have 5 actions, I will have 5 values. I will have the value of each action in this current state. Then the reason we are doing this is because it's possible to have more than one optimal action. Maybe there are 2, 3 actions, they are equally high or equally good. All of them are, for example, have the same value. So it's not just one maximum action, but we can have 2 or 3. How do we deal with that? We have to choose randomly one among these actions. So because otherwise it's easy, just choose the maximum action from this table. So we can initialize this to 0, and then what we'll be doing is we have to iterate through the action values, and we have, for example, 4 actions, 4 values. And for each one of them, we're going to check if it's equal to the maximum. If it's equal, then we're going to add it to the list of the best actions, okay? The top actions. So argmax action is the list that contains only the best actions, the actions that are all maximum. And among those actions that happen to be the maximum, we will choose randomly one of them, okay? So this is called brick and ties. Execu, I think in French, when you have 2 winners and then you just flip a coin to choose who wins, right? At the end, like when you play World Cup and everything is the same, all the scores, the points, the goals, the difference in goals, then what they do at the very end, they just take a coin and you say you are the winner, right? Just by chance, okay? Yes? Yeah, for example, yeah. Okay, so did we implement this? Yeah, question? Not yet, not yet. Get in there. We are already half the code. Now we go to the second one, and then what you are saying is what we do in the function learn, which is the last thing to do. Okay, so let's take care of the second case. Let's write this code quickly and make sure that you don't have typos. And then we'll explain it, and then the last one, and then we'll execute the whole thing. So please write down the else case. Okay, I think this one, who wants to volunteer quickly for just quick explanation? Yeah, you? Or you have question? Okay, come ahead, please.
So here we are in the second choice where we have to choose a random action. So here after some time of learning, we will be totally rational. Here, for example, if epsilon is greater than 0, we will decrease epsilon each time this value to, and at the end, for example, after I think 1,000 step, it will be the value of epsilon will be 0. So here it will be the choice will be totally rational. So we will all the time choose rationally the next step.
Okay, thank you. And I will try to make this clearer. So, okay, so we'll explain this. So this is the case where you want to try something completely new, something that doesn't make sense to you, really. It's not because it's the best, but sometimes you want to do this, okay? So 90% of the time you want to do this, to do the best thing, and sometimes you want to try random things. So when we get here, if because of the sampled variable, if it happens to take us here, then what we do is very easy, just this line. The next action is going to be a random action among the list of all the actions that we have. And then what we have here is less important. What we have here is just decreasing the exploration probability. So as long as the epsilon is a probability, right? It's the probability of doing random things. As long as it's positive, it will keep decreasing. It will be decreasing by very small amount. Because at the beginning, you want to try a lot. When you are a child, you play a lot. When you grow up, you want to do the right thing, the rational things. So this small epsilon, this high epsilon means playing, means the agent is playing to discover the world. So, and then as you get older, as the robot is getting older, this epsilon is decreased gradually until you just do, because you know what you should be doing. So, and well, at some point, let's say your epsilon becomes negative. Doesn't make any sense. So put your epsilon back to 0. That's what this is saying. If your epsilon becomes too small and then you decrease it and becomes negative, then put it back to 0, and means that you are not exploring anymore. Okay. When it gets to 0, that means that you are just doing the optimal thing. You will never, because when epsilon becomes 0, then this condition is always verified. All right. And then, all right. So we are done with that. So did you write until return next action, I guess? We're gonna write the last, so there is nothing here actually. This is just something we can delete. So actually it's just this last part. Let's write it and I will explain it myself. And we're gonna run this code and you will see how it's learning. Yeah. This thing is just a brick of the line, right? You can ignore it and it just breaks on the line, yeah, because it's too long. So So there are only 3 instructions here. There is this one, there is the second one, and there is this last one. 3 lines of code. Okay, one more minute, and we will run everything. So. I hope this is not confusing people. This is just one table that has 2 dimensions, next state and next action. It's just the same. I think I can just do this. You see, there is a reason why. Okay, just keep it as it is. Okay. Volunteer. Champion. You want to do it again? Okay, sure.
All right. Everyone.
Okay. Explain, yeah.
Okay, for the first line, next action is defined by, it's equal to the argmax of the Q table. So what we are doing here is to select the best action to do.
We are not choosing the best action to do here. Here we are just learning. We are not choosing anything here.
Oh.
We are just learning. We are in some state, right? And we choose some action. We observe the reward, and we observe the new state. So we have new data. I just deleted something. Okay, so the new data is the following. This whole thing, current action, reward, and next state, this is an observation. So we can use this to update the Q value. So what we are doing here is just updating. And in order to update the Q value in the equation, we know that we're gonna need the best Q value of the next state. Yeah. Explain it more clearly.
From the table, like in the example of the drone, when we have different rewards, we choose the one with the max reward. Is it now clear? No.
Yeah, it's if you I think maybe I can open just the perfect. This is what we are doing here. We are starting from here. First instruction is doing this. It's looking at the next state and picking the best value and back propagating it to the current state, okay? By using this update equation. So first line is calculating this operation.
Yes.
This is this. Take the max at the next state, okay. And then,
I think there is someone who has a question.
Sure, yeah. For exploration? Here? Epsilon is just used to decide what to do, and then for the update, we don't care about epsilon anymore. Okay? So we use epsilon to say if we're going to do the best thing or something random, then we do something, and then we update the Q values based on what we did. Okay? It doesn't appear in the update. It doesn't play a role. It appears only when you want to decide what to do, right? Okay, go ahead. Second line.
Oh, I was going to explain
Yeah, yeah.
first.
Oh.
The max when
We are done with first line. Second line.
So now we have the. Can I go back to the formula, please? So here in the formula we have the current state. So we had 1 minus alpha, which is calculated here. Here, self-reference. So what we're doing is, in the first line we calculate the max of the current state, and now we calculate the rest of the formula, which is basically this part. So what we are doing, so in the next, the previous state, we update the Q values. I don't know if I'm really clear about it.
Do you want me just to finish this? Okay, sorry. I think you are a little bit nervous, maybe. It's okay. But thank you very much. That was very good, first part. Okay, I'm going to finish it. But thank you. So the second thing is this. I'm going to compute this part, which is the reward plus gamma times the max. So I'm going to do all that. I'm going to take the reward plus the gamma, the discount factor, and gamma is something fixed, like 0.9, times this thing, which is the Q value of the next state, and the next action. And next action is already the maximum one. Okay. So the second line is just doing this: reward plus gamma times the max Q value of the next state. Okay. Now that I have that, what do I have to do? I have to multiply it by alpha and add to it the old value that I had multiplied by 1 minus alpha. Okay? So I have to multiply it by alpha. Okay, the new one is multiplied by alpha. And the old one, which is what I have already stored in my Q value table, will be multiplied by 1 minus alpha. We are done. So now, try, if you are done with that, we can, if you have no question, we can go to the main code and run this. Yes? Yes? Sorry, which one? Yeah. Yeah. So it's just matrix that has state and action, and we update this thing. So, is there another question, or can we go back to the original code now? If you wrote this carefully, we'll give it a try and run it. So that's what you had at the beginning. Now we don't need that. Let's see. So we're going to go to run by, and this is what I want you to write here. Actually, I'm not sure if you have that. Okay, let me see. So I think there was something that I commented from here, right? There was Qlearn. Which one is commented in the code that I gave you? Learn and print, exactly. So now at least increment learn, okay, and run. Okay, so uncomment where in your code that I gave you, make this line 19 uncommented such that it will be executed, learning, and execute the same thing and tell me what you have. Okay, so just uncomment again. This is the last thing we're going to be doing, because now you implemented Qlearning, and to see the result and the fruit of your work, uncomment line 19 on your main code. Remove the comment, remove this hashtag from it, and you have something like that, right? You have. I gave you code that has this. Do just this, and run the code and tell me how it's working. And meanwhile, I'm going to prepare, because I have kind of messed up code here, I'm going to prepare it and run it also here. And if you notice anything about my criminal activities, please don't report me. Just kidding. We can talk, maybe it's less, it's more tricky question. I want just to make sure that people have things working, right? That's the most important thing. I will be here for people later if they have some questions. But is it working now? Cool. Who has it working? Is it learning? Who has it learning? That's pretty cool, okay. I don't even have to do anything else. I think my job is done. So who doesn't have it working? 1, 2, 3, 4, 5, 6. Why? Do you have a bug? Is it making error? So this is how I'm gonna solve it. I'm gonna email you right now the correct code, and you will figure out where is the problem. Okay? But before doing that, I'm not going to open my Gmail account in front of you because you're going to report me for my criminal activities. So I'm just kidding, of course. So I just emailed everyone right now the answer, the code. So compare your code. For those who didn't make it work, compare your code, and most likely you just miswrote something, okay? And it's pretty good because we got, like, I think most people got it learning and working. So people who have problem, maybe I can give you feedback. Why people who didn't manage to make it work? Is it a bug? Is it like breaking somewhere? Python bug? Or is it working but it's not doing what it's supposed to do? Question for people who didn't make it work. Can you tell me where you suspect? What do you want me to show you again? I can show you some part of the code again. It's all here. Yes? Okay, I will go just quickly over, try to help people. Okay, one thing to make sure that it's working, let's do the following. Go to where we have sleep and make it very small to make it run very quickly, all right? And then we'll see that it's actually getting quickly to the right thing. Okay, I will show you this very quickly. MLSS Algiers, okay, let's see that. Grid word. Environment. Okay, so where do we have, so open this file. Okay, open this file, environment. Okay, and then here, change this sleep and make it very small. Where is sleep? Sleep, it means pause. Okay, so you have here sleep, which is half second. Let's make this super small, and just any small number such that it runs very quickly. And then here, make it also super small. And then run it, and this should be running very quickly. So we can do this, I'll show you. Okay, this is just different visualization, but same problem. Just change the image. So this is exactly the same thing, but I was using different image here. Now it learned, almost learned. It's still learning a little bit. So this is what you should be observing, that the agent is going around the obstacles to get to the goal directly. Okay, I can show it with the exact same image that you have. Okay, question, did you observe this behavior going around and to the goal in your code? Good. Wow. It works. Yeah, cool. So I will send you the whole code. So I'm happy that it went well. I think we should then stop here. Questions maybe, yeah, general questions, and then we'll be done. Yeah, it takes several to convert. So depending on how you change your alpha, it may learn quickly or slowly. It depends on the problem. Questions, questions. Questions, yes. Yeah. Yeah. If okay, I will explain just in general the answer. So this is what we call tabular Qlearning, which means that each state is treated separately, each state, each action. But if you have a lot of states, like in chess, or continuous state space, you cannot define your function as a function of the state. You cannot have Q tables. What you need to have is a function of the state. You need to write your Q as linear function of the state, or features of the state, for example. Okay, so you take your state, you don't work directly on the state, you extract features, like for example, distance to obstacle, distance to goal, anything that you care about, and then you say that my Q function is linear combination of the features of the state. And then what you will be learning is not these Q value numbers, like the Q values that you see here, but you will be learning the weights of the features. And then if you want to go deeper, then you can use deep network. Instead of using linear weights, you can use linear of linear of linear, and you get maybe deep network. Okay, so now you learned about reinforcement learning. So actually, this is my last lecture here. I'm flying tomorrow morning. It was a pleasure being here, and I think that's all for today. Maybe Ahmed wants to close the day with some remarks. Or you're welcome.